name is Christian, and I am a member at KGSEA Math Circle. And today I'll be presenting on convolutional neural networks, or CNNs. CNNs are one of the most powerful tools in deep learning, especially when it comes to analyzing images and visual data. So first, what is CNN? A convolutional neural network, or CNN, is a type of deep learning model designed to process grid-like data, for example, images. Unlike a regular neural network, which treats input as one long vector, CNNs preserve the spatial structure of the image. This makes them much more efficient and scalable. For example, an image of size 32 by 33 with 3 color channels would need over 3,000 connections if fully flattened, but CNNs use local connections instead, vastly reducing the parameters. Then, to understand CNNs better, let's contrast them with regular neural networks. A traditional network takes an input vector, passes it through hidden layers, and outputs class scores. The problem is, when dealing with large images like 224 times 224 by 3 color channels, a fully connected approach explodes in the number of parameters, making training inefficient and prone to overfitting. This is where CNN comes in. They scale much better for large image data too. So this is the components of a convolutional neural network, and CNNs are built from a few core building blocks, as you can see here. First, convolutional layers, which extract features from images. Second, ReLU layers, which introduce nonlinearity. And third, pooling layers, which downsample and reduce dimensions. Last but not least, fully connected layers, which map the learned features into predictions. These layers work together to transform raw pixels into a output. To be more specific with the architecture overview, the input layer is basically the image that we are trying to train, which holds raw pixel values like 32 times 32 by 3, which we will be using in this case. The convolutional layer applies filters to detect edges, textures, or shapes, giving us something like 32 by 32 by 12. The ReLU layer applies the function max 0, x, keeping the size the same. The pooling layer downsamples the data, for example, from 32 by 32 to 16 by 16. Finally, the fully connected layer outputs class scores, say 1 times 1 times 4 for 10 different categories. This pipeline is the foundation of most CNNs. So the convolutional layer is the heart of a CNN. It works by sliding small filters or kernels across the image and computing dot products. To be more specific, the filter in this case, as you can see in the middle of the slide, has 75 values, as it is 3 times 5 times 5, which we will be using today. This filter, as you can see here, has different values for each pixel. One thing to note is that the depth of the image is the same as the depth of the filter. Then the filter will be convolved with the image, sliding over the image spatially, meaning that it will start from the top right corner, moving 1 pixel by 1 pixel all the way down to the bottom left corner. Since the depth of the image and the filter matches, the filter will perfectly match with the image when convolved. The filter then will perform pixel-wise multiplication for each 75 overlapped value, meaning that the value of the filter and the overlapping value on the image will be multiplied. This value equals 1 box on the right. And finally, when the filter reaches the bottom left, all the multiplied values will be summed up to turning into an activation map, as you can see in the right slide. This would have the dimension of 1 times 28 times 28, which with bias included. This process of getting into activation map will be repeated with multiple times, having different filters every single time. For example, in here, instead of the blue filter, we will be using the green filter, and each filter specializes in detecting a certain feature like vertical lines, curves, or textures. Yeah, and then we will be repeating this several times and making a whole block. As layers stack, the network moves from detecting low-level features like edges to high-level features like shapes and eventually object parts. This process produces what we call a feature map. And this is a simple summary of the entire process. Next up is ReLU layer, which comes after convolution, and we apply a nonlinear activation function. The most common activation function that we use is ReLU function, also known as rectified linear unit function, which simply sets negative values to 0 and keeps positive values. As you can see in the graph, all the negative values will be at 0, while the positive values will be kept. This helps the model learn more complex patterns. Without activation functions, our network would just be a linear transformation and couldn't capture real-world complexity. Next comes pooling. Pooling reduces the spatial dimensions of the feature maps. For example, max pooling takes the maximum value from a region, shrinking the data size but keeping the most important features. For example, in this image, we see a 4 by 4 square with 16 different numbers, and each 4 of them are colored with different colors. By doing max pooling, we will be choosing the biggest number from each color and turning it into a 2 by 2 filter, being able to downsample the input. Finally, after convolution, activation, and pooling, we flatten the data and feed it into fully connected layers. These layers act just like a regular neural network, connecting every neuron to the next. At the output, we typically use a softmax function to assign probabilities to different classes. For example, in the CIFAR 10 dataset, the output might be 10 scores representing 10 categories like cats, cars, or airplanes. CNNs are everywhere today. In image recognition, the power systems like Google Photos or Facebook's face recognition. And also in medical imaging, they help doctors detect tumors from X-rays or MRIs. In self-driving cars, CNNs identify lanes, pedestrians, and traffic signs. And lastly, in security, they are used for surveillance and biometrics. Beyond images, CNNs can process speech, text, and even time series data, showing their flexibility. This widespread use is why CNN is considered a breakthrough in AI. Looking ahead, researchers are working on ways to overcome these challenges by using transfer learning, which allows us to reuse pre-trained CNNs instead of training from scratch. New architectures like REST nets and mobile nets improve efficiency and accuracy. And most recently, vision transformers have emerged, sometimes outperforming CNNs. In fact, many modern systems combine CNNs with transformers to the best of both worlds. To summarize, CNNs process data in a way that preserves spatial relationships. They use convolution, ReLU, pooling, and fully connected layers to gradually extract and refine features. They have revolutionized computer vision and are now applied in many domains. Thank you for listening. This is my citation.